Welcome to the second video of this module. In this video, what we're going to do is define and see how we can recognize the difference between deductive argumentation and inductive argumentation. In terms of this class, this video is going to cover basic concepts that are found in Chapter 1, Section 1.3 of the textbook. This is one of your assigned readings, and you'll have homework over this information. What I plan to do in this video is elaborate on and explain the basic ideas that you're looking at. So the first step in all of this is to recognize that arguments come in basically two broad different classifications or types. Any argument that you have, regardless of what it's arguing, what the content is about, or the like, will fit into one of two categories. The first possible classification of arguments is deductive argumentation. The second classification is induction or inductive argumentation. Now, our basic goals in this entire section of the course and in this video is to first define each of these argument classifications in clear and detailed ways, and then second, to determine how one can sit down and recognize and ultimately distinguish between these two different classifications of arguments. In other words, the basic goal here is that you can sit down with an argument and very cleanly place it into its appropriate category. That is, you can say this particular argument, for example, is inductive because it's arguing by analogy, and this particular argument is deductive because it is a disjunctional syllogism or the like. Now, it's worth noting that this class, formal logic, deals exclusively with deduction. So for our purposes, we are introducing induction as a classification of arguments that we're not going to deal with, that we can distinguish from deduction. Our primary concern is deductive argumentation. Now, this does not mean that induction is valueless or not important. In fact, it's incredibly useful stuff. It's worth your time studying if you're interested in it. And in fact, in your book, there is one chapter, actually two, but one chapter that is focused on this, chapter 3. If you're bored and you're looking for something to do on the weekends, you might consider studying that particular information. But again, our course, Formal Logic, is exclusively addressing deductive argumentation. So let's start in on deduction, and again with the goal of figuring out precisely what deduction is and how we can tell that a particular argument is in fact a deductive argument. So let's define deduction. So here's a working definition of deduction. A deductive argument is an argument in which the arguer claims, or it is implied by the kind of reasoning that the arguer is using, and that is a more probable way of looking at it, that it is impossible for the conclusion to be false given that the premises are true. Now again, the basic claim here is a deductive argument is one that claims that it is impossible for the conclusion to be false given that the premises are true. And pay attention to that term, impossible. So here are the basic characteristics of deductive argumentation. First of all, in a deductive argument, if the argument is properly formed, then the conclusion follows necessarily from the premises. In other words, if the premises are true and the argument is what we call valid, which is a concept we'll have to work on here, then the conclusion must be true. It has to follow from those premises. So what we're looking for in a deductive argument are necessary conclusions. That is, if you accept all the premises are true and everything is formed correctly in the argument, then the conclusion simply has to be true. So the connection here between form and validity is going to be very important for us. Validity is a term that's going to be central to the entire class and everything we do in it, because ultimately that's what we're concerned with. We will define this in the next chapter of the book and in the next video, and we'll spend some time trying to make sense of it. But for now, it's good to recognize that validity is really a function of the form an argument takes in deductive reasoning. So we'll come back to this. Now, here's the basic idea that we're getting at, though. Take this particular argument. It says all politicians are liars and all liars are sinners. Therefore, all politicians are sinners. Now, if you stop and think about this argument for a minute, if it is true that every conceivable politician without any possible exception is in fact a liar, and it also turns out that every conceivable liar without exception must be a sinner, then logically speaking, it has to be the case that every conceivable politician without exception must be a sinner. Now, if there's a problem with this argument, it's not with the reasoning here. It might be that our particular claims aren't true. Maybe not every politician is a liar, though I personally have my doubts. And it might not be the case that every liar is a sinner. But if we accept these particular premises to be true, then it would follow necessarily that every single politician without exception is a sinner. Now, why it works like it does, why deduction gives us necessary conclusions, is essentially that in a deductive argument, all we're doing is making explicit information that is concealed in the facts that we already accept as true, that is, in our premises. So the conclusion contains no new information, no information that isn't already present somehow, either explicitly or implicitly, in the premises in the argument. So let me give you an example that might show you what I mean here. Take this particular argument. The cat is sitting on the rug, therefore the rug is underneath the cat. Now notice, if you accept the first claim, the premise that the cat is sitting on top of the rug, then you really have to accept as true the second claim, which is the rug is underneath the cat. And the reason for this is really simple, because the premise is really just telling you the same thing as the conclusion. Right? When you say the cat is sitting on the rug, what I mean by sitting on in this particular case is that whatever's doing the sitting has the thing it's sitting on underneath it. So these two claims are basically just telling you the same thing. The conclusion hasn't really moved beyond the scope of what we already know implicitly or explicitly in the premise that's given there. And while this is a more obvious example, this would also be true of the first argument we saw of all politicians are liars and all liars are sinners. In the end, the conclusion that all politicians are sinners is ultimately not giving you something new and different that isn't already contained somehow ultimately in the premises that you have. Now, the last point to make about deduction in terms of basic characteristics is that deductive reasoning is what we call analytic in nature. And what this means is that it does not require any reference whatsoever to the external world to be valid, right? Now, again, we haven't defined this term validity yet, and we will, a very important concept. But essentially, we might say that validity means it's a good argument, right? Or it's reasoning well. And a valid argument is dependent merely on the form that the argument takes and nothing else. So what this means is if we take a look at something like our first argument, that all politicians are liars and all liars are sinners, therefore all politicians are sinners, why that conclusion follows actually has nothing to do with politicians, liars, and sinners. That is completely irrelevant information. What matters is how the argument is formed. The basic structure of this reasoning is that every A is a B and B's are always C's, therefore A's are C's. And notice, politicians, liars, and sinners are simply filling in that basic form, and it's because of the form that that conclusion follows. We could literally plug in anything for A, B, and C here, anything, and it would still follow necessarily. It would be a valid argument. So if I said all apples are basketballs and all basketballs are carrots, therefore all apples are carrots, this would follow necessarily from those premises just as readily as the original argument about politicians, liars, and sinners. And if you stop and think about it, if it were true that every apple without exception was a basketball, and it was also true that basketballs are always carrots, then necessarily apples would have to be carrots too. Why it works like this, again, has nothing to do with the content. What A, B, and C stand for is simply irrelevant. What we have is a basic kind of structure. If every A fits into the B's and every B fits into a C, then necessarily A's are going to be C's. That's just how it works. Now, there are different types of deductive arguments, and as we'll see as we wade through this quarter, things will get far more complicated than we'll introduce in the first module. But what we want to do at this point is kind of wade through the various distinctions here to define various types of deductive arguments. And again, our fundamental goal here is to get you into a position where you can look at an argument and recognize that that's what you're looking at. You know that this is deductive and it fits into a certain classification of deduction. So here's a basic list of types of deductive arguments. It is not a complete list. We'll see as we move on through the quarter that there's going to be more to this, and it gets far more complicated than this. But here are the basics. So we can start with deductive arguments called arguments based on mathematics. There are arguments that are based on definition or from definition. And then we get what is called an immediate inference. And then finally, we get what is really the workhorse of deductive reasoning, where most of deductive reasoning happens and where most of the important things in deductions will happen. We get what is called a syllogism. And for now, we're going to look at 3 different types of syllogisms. And again, with an eye of trying to figure out precisely how we can define these things and how we can identify them when we come across them. So we have categorical syllogisms, hypothetical syllogisms, and disjunctive syllogisms. As we'll see, we can add to this list ultimately by the end, but for now, this is what we're going to look for, and this is frankly what you'll be held accountable for in the first test. So an argument based on mathematics is pretty much exactly what it sounds like, and these are fairly simple, or at least they can be fairly simple arguments. An argument based on mathematics is an argument in which the conclusion of the argument depends purely on arithmetic or geometrical computations and measurements, and nothing more. So here's an easy example of such an argument. This argument says there are 32 books on the top shelf of this bookcase, 12 on the lower shelf of the same bookcase, and no books on any other shelves. Therefore, there must be 44 books in total on this bookcase. This is basically a simple math word problem. And the conclusion, of course, is that there are 44 books in total on the bookcase. Now this follows, and it follows necessarily for the really, really simple reason that 32 plus 12 plus 0 is 44. So notice the entire argument here is simply grounded on mathematics. And anytime you come across an argument that is just driven by mathematics of any sort, this has to be deductive because mathematics is fundamentally analytic. Here's another example. It says each bag of potato chips costs $2.50, and given that I want to buy 10 of them, it seems I will need more than $20. Now notice the conclusion that I'll need more than $20 to buy what I want follows, and it follows necessarily because $2.50 times 10 is $25, and 25 is greater than 20. So again, what we have here is reasoning that is just fundamentally driven by mathematical reasoning. So anytime you come across mathematical reasoning, then you should start thinking deduction. Now, for what it's worth, this is not something that we're going to do in this class at all. And in fact, for the most part, what we'll see is we're going to talk about this now, and then we'll never talk about it again. So the next type is also like this. This is deduction, no doubt. It's important in its own right, but it's not something that is really part of this class, and it doesn't fit very cleanly into formal logic. Nonetheless, it should be mentioned. The next type of argument, or deductive argument, is an argument from definition. So an argument from definition is the kind of argument in which the conclusion depends merely on the definition of some word or phrase used in the premise or conclusion. In other words, the conclusion is basically going to tell you exactly the same thing, and all it does to tell you that is define some particular word or phrase that is used in the premise. So let me give you an example. Cigarette smoke is a known carcinogen, therefore smoking cigarettes can cause cancer. Now notice our conclusion that smoking cigarettes can cause cancer has to be true if the original claim is true, the premise is true, which is cigarette smoke is a carcinogen. Now the reason it follows, and it follows necessarily from that premise, is because what we mean by a carcinogen is simply something that causes cancer. In the end, this argument is just saying because cigarette smoke can cause cancer, therefore cigarette smoke can cause cancer. And of course, if that premise is true, then the conclusion has to be true too. Now, these kind of arguments are somewhat trivial, but they are deductive and they are worth paying some attention to. Here's another example, one we've already seen. the cat is sitting on the rug, therefore the rug is underneath the cat. Now again, notice if you think about it, that premise that the cat is sitting on the rug, in a sense, already analytically contains the idea that the rug would have to be underneath whatever's doing the sitting. Because what I mean by definition is that to be sitting on means what you're sitting on is underneath you. That's what it is to sit on something. So in a certain sense, the premise is really not giving you any new information, right, that isn't already contained in the conclusion and vice versa. These are basically telling you the same thing. Now, an immediate inference, unlike the first two, is going to be something that we spend time with. This is an important type of argument, but it is minor in comparison to the syllogism. So we'll spend a little time here dealing with this. The focus in the first module will tend to be on syllogisms almost exclusively when we talk about deduction, but it's worth getting this out of the way and dealing with it. We will come back to it with a vengeance, and you'll probably end up hating these, but here you go. An immediate inference is the kind of argument that consists of only two propositions and where a conclusion is drawn directly from one premise without the mediation of a second premise. That's why it is immediate. There isn't a mediating second premise to get us there. Now, this definition is a bit ambiguous, so it's probably easier to simply show you what I mean by way of example. So take this example. It says, given that we know the claim some toads are green is true, we can also conclude that the claim no toads are green must be false. Now notice what we have here is a single premise, some toads are green is true, and from that we draw the conclusion that no toads are green has to be a false claim. They can't both be true at the same time. Right? Another example of this, since human beings cannot live longer than 200 years, anything living that is over 200 years old cannot be human. Now notice, if the first claim is true, human beings are never going to live longer than 200 years old, then it would also have to be true that anything that is over 200 years old cannot be a human being. One necessarily implies the other. Now, we'll deal with these in more detail much later on in the course or in the next main chunk of the course. For now, we can kind of gloss over these and move on. The best thing to note about these is, first of all, that the terms have a tendency to repeat themselves in any type of immediate inference. Notice in this particular example, we have human beings and things that live 200 years, and then it repeats itself in a different order in this case, living things over 200 years and human beings. So there's a kind of repetition of terms, and in the end, there's just a single proposition that leads immediately to a single conclusion. As I already mentioned, the syllogism is really kind of the workhorse of deductive reasoning. So this is where we're going to pay most of our attention or spend most of our time in this first module. As we'll see, it will get more complex than merely this as we wade through the quarter, but the syllogism is really a central and very important aspect of deductive reasoning. So what we want to do at this point is define different types of syllogisms, some of the basic core types of syllogisms, and then from there we want to see how do you recognize what it is you're looking at. In the first module and on the first little exam you have, you can pretty much expect to be focused on syllogisms or recognizing syllogisms in deductive reasoning and not really the other parts of this. So a very basic definition of a syllogism is that it is a deductive argument in which a conclusion is inferred from two premises. Now this is quite basic in terms of the definition, and as we'll see, we'll have to add considerably as we wade through different types of syllogisms. But there are two basic points that need to be recognized here that will be true of any syllogism regardless of what type it is. The first is that syllogisms are always deductive, which means that if you see the term syllogism, you should start thinking about deductive reasoning, not induction. The second is that syllogisms will always have two premises and a single conclusion that follows from those two premises working together. Now, you can have syllogistic reasoning that is more complicated than this, but in the end, what you really have is multiple syllogisms that are working together to get us to conclusions. A single syllogism by itself and isolated from other arguments will always have two premises and a single conclusion. Now, there are three different types of syllogisms that we're going to look at in this particular module, and then we'll stop there. We can add to this later. The first is called a categorical syllogism, the second is a hypothetical syllogism, and the final one is a disjunctive syllogism. And our goal here again is to get you into a position where you can look at an argument and understand precisely what you're looking at. You can point out to an argument and say, this is deductive because it's a categorical syllogism, or this is deductive because it's disjunctive. So let's start with categorical syllogisms and try to define basically what it is that makes a categorical syllogism categorical. Right? It's a syllogism, which means, of course, that it has two premises and one conclusion, and it's a deductive argument. So what is it that distinguishes it as a categorical syllogism? Well, a categorical syllogism is a deductive argument that consists of three categorical propositions that contain exactly three terms in total in the argument, and each of these terms occurs in exactly two of the propositions. So we'll find that the terms will repeat themselves. So basically what we get is something like this. This would be a standard form categorical syllogism devoid of actual content. So whatever S, P, and M stands for, who knows? You can plug in whatever you want, dogs, cats, and mammals or something. But what we have here is all P's are M's, all S's are M's, and all S's are P's. So the basic defining characteristics here are this. First of all, notice you have two premises and a single conclusion that follows from it. Remember, our premises are listed in order on top. There's a line separating them from our conclusion. Every statement here is what we call a categorical proposition. Now we're going to take a moment here to explain exactly what categorical propositions are, and we'll do that in some detail in a little bit here. But for now, just recognize that all the way through the argument, every single statement, both premises and the conclusion are categorical propositions. And the last point to note is that in the total argument constructed in this way, what you will always find, if it's a good categorical syllogism, is a repetition of these terms. Notice how in this particular argument I have two different S's, I have two different P's, and I have two different M's. This repetition is precisely what makes a categorical syllogism work, as we'll see in a minute here. But keep in mind, this is a basic feature of a categorical syllogism. Look for repetition of terms. That is a really good indication that you're looking at syllogisms in general, and in particular categorical syllogisms. So let's figure out exactly what a categorical proposition is, because a categorical syllogism is built entirely out of these things. So we need to understand precisely what they are and what they're doing. So a categorical proposition is a statement that asserts a relationship exists between different categories or classes of things. So to make sense of this, let's go to some examples. Here are some easy examples of categorical propositions. All dogs are mammals. Some athletes are runners. No eagles are herbivores. Some airplanes are not jets. Now notice what you get in every one of these cases is I make a very distinct claim, like all, about one class or category of things, in this case dogs, and I assert that it has a relationship to a different class or category of things, mammals. So this is what categorical propositions do. They take one class or category and it asserts there's a relationship that exists between that first class and some other different class. Dogs to mammals, athletes to runners, eagles to herbivores, and so on. So we can distinguish between different propositions, categorical propositions, by looking at the quantity of the claim and the quality of the claim. The quantity of the claim is essentially asking how many of the first category are we talking about. The quality of a claim is saying what kind of relationship exists between these two different propositions. And again, let's walk through some examples to try to make this clear. So in standard form, it turns out there are only 4 possible types of categorical propositions. Any categorical proposition, no matter how messy or complicated, can ultimately be smushed down into one of these 4 basic forms. All are, no are, some are, and some are not. That's it. There are no other options available to us. So it's all are, no are, some are not. Now these 4 possible variations on the categorical proposition can be distinguished from one another both in terms of the quantity of the claim being made and the quality. Remember, quantity is saying how many, quality is saying what kind of relationship is it. So if we want to talk about quantity, there are basically two different options. The first is we can be making a universal assertion. Remember, quantity is saying how many of the S term in this claim are we talking about that has some sort of relationship with the P term. If it's a universal claim, I'm saying every last S in existence, no exceptions. Or I'm saying absolutely no S's, no exceptions. So universal claim is the all claim and the no claim. And they're basically telling us every single S without any exception fits into the category of P or not. On the other side, in terms of quantity, we can have what are called particular claims. Now, a particular claim is basically a some claim. Some are or some are not. Now, when we talk about these, what we mean, the universals basically all and no are saying every single member of the category would be an all claim. No members of the category, absolutely none, would be a no claim. Some is going to be our tricky one. When you say some, what we mean is there is at least one member of that category. That's all we mean by that. It could be more. It might be 2, it might be 10, it might be 10 million, and it might even be all of them. But all I'm asserting by a particular claim, a some claim, is there is at least one. Now, this is going to be very important when we get into categorical reasoning. So pay attention to that idea. And for now, when you see a some claim or something that translates into a some claim, start thinking there is at least one. Maybe all, but there is at least one. Now, the quality of a claim is, again, answering the question, what kind of relationship exists between the first category and the second one? In this case, between the S and the P. And there are two options here as well. An affirmative claim, the all and the some are claims, these work to basically assert that the S and the P somehow go together. Remember that quality is saying what kind of relationship is there, and this is basically kind of putting together. When I say all S's are P, I mean every single S has to fit into, goes with the category of P. When I say some S's are P, I'm saying there's at least one S out there that fits into or goes together with the P. So affirmative claims are kind of putting together those two different categories. On the other side, we get negative claims. And if affirmative claims are putting together, negative is simply taking apart. And of course, the negative claims should be pretty obvious. This is the no claims and the some are not claims. And notice what we get with a negative claim is I'm saying, when I say no S's or P's, I'm saying S has no relationship whatsoever to P. Those two categories are always separate from one another. They're taken apart. And if I say some S's are not P's, I'm saying there's at least one S that does not fit into, that is taken away from the entire category of P. So the basic distinction between affirmative and negative, in terms of answering the question, what kind of relationship is it, is pretty simple. Affirmative is asserting that the two categories go together. Negative is asserting they go apart or they're separate from one another. Now notice what this means in terms of quantity and quality. Categorical propositions come in only 4 possible variations. We can have universal affirmative claims, universal negative claims, particular affirmative claims, particular negative claims. A universal affirmative is saying all S's, every single S without exception, goes together with P. A universal negative claim is saying absolutely no S without exception. S's are never going to go together with P. They're separate from one another. A particular affirmative says there is at least one S in existence that fits into or goes together with the category of P. It's affirmative. And a particular negative is saying there's at least one S that does not fit into the category of P, that is separate from it. And again, there are only 4 possible types of categorical propositions. Any categorical proposition you find, no matter how it's expressed, will ultimately fit into one of these 4 models. So, what is a categorical syllogism, and how does this kind of reasoning work? Remember, the first thing to note about this is that they're constructed entirely out of categorical propositions. In this particular case, I have 3 universal affirmatives. All M's are P's, all S's are M's, therefore all S's are P's. Now notice what I'm trying to do in the conclusion. So if you think about this argument, the conclusion is trying to assert that every single S in existence has to fit into the P category, that those things always go together. That's what I'm trying to prove to you. And the evidence that's given is essentially that S has a distinct relationship to M, and P also has a relationship to M. It's because S and P and the premises are connected by way of that middle or shared term, in this case M, that we can actually just put S and P together. Right? And this is basically what a categorical syllogism does. This is also why it's incredibly important that the terms repeat themselves. If I don't see my terms repeating themselves, then I can't put it all together into this basic structure. So let's take a look at a very simple example of a categorical syllogism. Now, as we go through these few examples, do not assume that these are good arguments. Right? In this particular case, this argument is actually not a good argument. It's invalid. But it is still a categorical syllogism, and it is attempting to give you this kind of reasoning. So it still functions as a model for what we're looking at. So if we look at this, it says some athletes are vegetarians, and all football players are athletes. Therefore, some football players are vegetarians. Now, if we wanted to reconstruct this, the argument form will eventually look like this. Notice the conclusion here that some F's or V's is essentially the conclusion that some football players are vegetarians. And we can pretty much just start dropping the content. F will represent football players, V will represent vegetarians. This is the structure of this argument. Now notice what the conclusion is attempting to do. This argument wants to say we can prove to you that there has to be at least one football player in existence that is a vegetarian. And the reason for this, the argument that's given in defense of this claim of putting at least one F together with the category of V, is that every conceivable F without exception, it fits into the category of A, and there's at least one A that also fits into the category of V. So notice what it's trying to do, and in this case not really successfully, but it's trying to connect F and V together, football players and vegetarians, and what allows them to try to make that move to connect those terms or categories is that there is a shared term A sitting between them in the premises. The first premise connects A to V, vegetarians, or athletes to vegetarians. The second premise connects football players to athletes. Let's look at another example. This argument says no nuclear-powered submarines or commercial vessels, so no warships or commercial vessels, since all nuclear-powered submarines are warships. Now, if we take a moment to try to break this down and figure out the structure of this argument, the first thing you should note are your indicator words. Notice, first of all, the so suggests a conclusion is the middle claim, not the end, and sen suggests that that last claim, all nuclear-powered submarines or warships, is in fact a premise. So what is the structure of this argument going to look like? Well, the conclusion is no W's or C's, or no warships or commercial vessels. And if you think about what this argument is attempting to do, we are trying to say that we could never, ever, ever put W's and C's together. The W's will never fit into the category of C's. We could never have a warship that is also a commercial vessel. And the reasoning for this, why we think this should be true, is that W and C are connected in some way in the two premises by way of this shared term, by way of in this case. So W is connected to in, and C is connected to in. And so those two terms, W and C, we can kind of skip the stuff in the middle to smush them together at the end of the argument. Now, let's look at one last example of this. And this is a very good and important example for our purposes because the previous two examples are given to you in really blatant, clear categorical terms. They all start with all are, no are, some are, and some are not. But it turns out that we really don't speak or write like that very often. In fact, most of the time when we express ourselves categorically, it turns out that we don't use those kind of quantifiers to make clear sense of the kind of claim we're making. Instead of saying all dogs are mammals, we say things like every dog is a mammal, dogs are always mammals. Instead of saying some dogs are basset hounds, we say things like this dog is a basset hound, a few dogs are basset hounds, and so on. So we need to be able to recognize when we're dealing with categorical propositions and need to recognize what it is to find and discover a categorical syllogism. So this is a very good example because it doesn't come to you given in really blatant terms. So this is from good old David Hume, and the argument he gives is this. He says, since morals have an influence on our actions and affections, it follows that they cannot be derived from reason, because reason alone, as we've already proved, can never have such an influence. Now notice again in this case, the argument is not given to you in really blatant terms, but there are some very good indications that you're dealing with a categorical syllogism. The first thing to note is that there are clear categorical relations given here. Morals influence. Morals are derived or are not derived from reason. Reason doesn't influence. This is a kind of categorical relation between these terms. It's also worth noting that my terms are repeating themselves. That repetition of terms is a huge indication that you're dealing with syllogisms, categorical in particular, but really any syllogism. Notice morals, morals, influence, influence, reason, reason. Everything repeats itself in the argument. So if we want to lay this out formally to see what it looks like, the first step is to figure out what our conclusion is. And notice he is kind enough to give us very clear indicators. The first claim he says since, the second one it follows that, and the third says because. So we have premise, conclusion, premise. The conclusion then is morals cannot be derived from reason. So to put this in more technical terms, this would be no morals are things derived from reason. Now, the argument then, if you think about it, he's trying to say morals can never fit into the category of things that are derived from reason. Those never go together. And his reasoning for this, how we can show that this has to be the case, is because morals have a distinct connection to reason through this shared term of things that influence our actions. Notice all of our morals do in fact influence. Reason doesn't influence, so morals cannot be the same thing as reason or derived from reason. So again, some telltale signs that you're dealing with categorical syllogisms, the things to pay attention to. First of all, look for blatant repetition of terms. When you see moral, moral, reason, reason, and so on, that kind of repetition is a good sign that you're probably dealing with a syllogism. Look for blatant examples of categorical propositions. All dogs are mammals, some dogs are basset hounds, no dogs are cats, and so on. When you see very clear assertions like that, where one class or category is being asserted as having a relationship to another, start thinking categorical syllogisms or perhaps immediate inferences. Notice too, you should always have two premises and one conclusion. And what you're looking for is that move from one term to another through a shared middle term in the premises. So that's a categorical syllogism. The next step here is to look at hypothetical syllogisms. Now, hypothetical syllogism is going to be a bit different than categorical in certain ways, but at the same time, there are things that are very similar. For example, there is a lot of repetition of terms. Now, a hypothetical syllogism is, first of all, a syllogism. So what that means for us is it's deductive, and it will always technically have two premises and one conclusion. This is true of any syllogism, whether it's categorical, hypothetical, disjunctive, or otherwise. So a hypothetical syllogism is a syllogism that has a conditional statement for one or both of its premises. So basically, this is a kind of syllogism that is built around or out of conditional statements. Now, what's a conditional statement? If you remember, we already went through this in the last module. A conditional statement is basically just an if-then claim. In standard form, what you will find is that a conditional statement will always have a basic structure. So if we take this example, it says, if you wash the car, then I will pay you $10. Notice this is a conditional statement, an if-then claim. And what we find basically is that we can start breaking this apart into different terms, and these terms have concrete labels. So notice the part that sits between the if and the then is going to be called the antecedent. So in this particular case, you wash the car is my antecedent. The piece that fits after the then, in this case, I will pay you $10, is what we call the consequent. So in standard form, a conditional statement will always be if antecedent, then consequent. And the antecedent and consequent will be their own distinct terms, the entire conditional statement in standard form will always run in that order: if, antecedent, and consequent. Now, the important thing to note about this is that the antecedent and the consequent are both what we call truth functional propositions. Now, what this means basically is that the antecedent and the consequent, being truth functional, are the kind of statements that we can reasonably understand as having some sort of truth value. They are, in other words, either true or they're false. If you look at the antecedent in this case, you wash the car, this is a true proposition or a false proposition. It's true if in fact you do wash the car. It's false if you don't. The consequent, I will pay you $10, is true if indeed I will pay you $10, and it's false if I'm not going to do that. So the important thing to note here is that the parts that make up our conditional statements are truth functional terms. And if you understand this basic idea, this will make sorting out hypothetical syllogisms and disjunctional syllogisms a million times easier. If you don't understand it, I would strongly encourage you to contact me and we can sit down and talk about this. But it's an important idea. It's one that's going to play a very central role in logic all the way through as we get into modern logic. But for now, keep in mind that our conditional statements are built out of an antecedent and a consequent, and these are truth functional. And all that means is that portion, the antecedent and the consequent, taken on by itself, is something that we can reasonably claim to be either true or false. Now, when we start talking about hypothetical syllogisms, remember, first of all, they're syllogisms, which means that they are deductive arguments. They will have two premises and a single conclusion, and they're hypothetical because they're built around conditional statements. There are going to be two broad basic types of hypothetical syllogisms. We have what are called mixed hypothetical syllogisms, which are incredibly important. They'll play a huge role in a lot of what we do over time here. And then we get pure hypothetical syllogisms. Now, to start with the mixed hypotheticals, a mixed hypothetical syllogism is going to have a single conditional statement as its major or primary premise. So basically what we find is that the first premise is essentially just a conditional statement, something like if A then C, and notice A and C represents an antecedent and a consequent, and each of those terms, the A and the C in this case, are truth functional. A is either true or false, and C is either true or false. So when we have a mixed hypothetical, there is a single conditional statement that is everything is built around. That becomes our primary and main premise. The second premise of the argument is going to work by either affirming one of the two terms, the antecedent or the consequent, as either true or false. So in this particular case, notice the first premise says, if A is true, then C is true. And the second premise says, well, A is in fact true. I affirm it as a true statement. And then the conclusion is basically going to do the same thing, in this case, affirm, to the other side of the original conditional statement. So what we have basically is an inference from these first two premises about, in this case, the consequent. The argument says if A is true, then C has to be true. And the second premise tells us that A is true. Well, if A is true, and if A is true, then C has to be true, then C has to be true as well. This follows, and it follows necessarily from the argument. Now notice we can have different forms of this. It doesn't always have to work by affirming. We can affirm or deny on either side. So notice here's another example. We have a conditional statement, if A then C, and again A and C are both truth functional claims. And in this case, notice what the second premise does. It says C is false. It denies. Now notice this little squiggle next to the C in the second premise. When you see that, we're saying it is not the case. So not C in this case, not the consequent. So the first premise says if A is true, then C is true. And the second premise says C is not true, it's false. And so the conclusion we would draw from this is that A can't be true either. Right? So essentially what we do with that original conditional statement is the second premise and the conclusion are going to play with those two parts. They're going to work by affirming and denying those parts in order. I affirm A is true so that C is true, or I deny C so that A is true, or vice versa. So let's look at an example of how such an argument will work. This argument says if a company is well managed, then it is a good company to invest in. Acme Incorporated is a well-managed company, and so Acme Incorporated is a good investment. Now, if we wanted to write this out formally, the argument's going to look something like this. Notice the first claim is a conditional statement. If W, then G. So if well managed, then good investment. The second premise says it is indeed well managed, and then the conclusion we can draw from those two claims put together is it must be a good investment. Now, if you think about this, the basic structure we're looking at is we have a first initial premise as a conditional statement with two terms, an antecedent and a consequence. And notice the antecedent in this case is W, the consequent is G. And those are truth functional claims. What will happen in the rest of the argument is that the second premise is going to pick one of those two things and then tell you it's either true or false. In this case, it takes the antecedent and says it's true. So notice the second premise resolves the antecedent by affirming it as true in this case. W is true. Therefore, the conclusion we can draw is that the other term has to be true too. If W is true, then G is true. W is in fact true in the second premise. Therefore, in our conclusion, G would have to be true. Let's take another example. It works in a different way. This one says, if our watchdog detects an intruder, then he will bark. But our dog did not bark over the whole course of the night, and therefore no intruder was detected. Now notice the basic structure of this argument. It begins with a conditional statement. If the dog detects, then it barks. The second premise comes along and picks up that consequent, that second term, and in this case it denies it. It says it's not true in order to deny the first term, the antecedent. So basically we have a first premise that consists of a conditional statement. If D, then B. And again, D and B, dogs barking, or detecting and dogs barking, are either true or they're false. The first claim says the dog detects an intruder. That's true if the dog detects an intruder. It's false if it does not detect an intruder. Now, the first premise is then the simple conditional statement with truth functional terms. The second premise is going to pick one of the two, the D or the B in this case, and in this particular case, they went for B, and then in this case, it denies it. It says B is not the case. The dog did not bark. And the conclusion we can draw about this has to do with the other term. So we can go to the first term, D, and we have to draw the same conclusion. It did not happen. So this says if it detects, then it barks. It didn't bark, therefore it must not have detected anything. So this is a standard way to think about hypothetical syllogisms, and in particular mixed hypothetical syllogisms. Let's take one more example, and this example is going to be useful because one thing it does for us is point out that we can have a syllogism even where not everything is stated explicitly. So this argument says, of course he's gullible. Anyone who takes horoscopes seriously must be very gullible. Well, notice in this case, it's not given to you in really explicit and blatant terms like we've seen in the other ones. If A, then B, A, therefore B, and so on. In this case, what we have is we have to do some translating and we have to fill in some holes. But if you stop and think about it, the anyone who takes horoscopes seriously must be gullible is really just saying, if you take horoscopes seriously, then you are gullible. So notice it's saying, if we wanted the structure of this, if you take horoscopes seriously, then you're gullible. And our conclusion, of course, is that he's gullible. Well, notice the second premise is simply implied. It's obvious that it has to be there. You couldn't get to that conclusion without it, but it's pretty clear that this person is saying he must take horoscopes seriously. So this argument basically says, if you take horoscopes seriously, then you must be gullible. He does take horoscopes seriously, therefore he must be gullible. And it does exactly what we thought it would. Notice the important point about this example is that the second premise is simply unstated. We're going to have that in order to get there. It's also worth noting that the original premise, number one, the if-then claim, is actually not given to you as a conditional statement. It's stated as anyone who. And we have to be able to convert that or recognize that that is essentially asserting a conditional relationship. Now, a pure hypothetical syllogism is going to be one that is built around conditional statements, just like a mixed hypothetical syllogism. But unlike a mixed hypothetical syllogism where there is a single conditional statement and everything else is simply resolving the parts of that conditional statement, in a pure hypothetical syllogism, everything is going to be a conditional statement. So basically what we find is the kind of argument we're talking about is one where both premises and the conclusion drawn are simply if-then claims. Right? So in this particular case, we have if A then B, if B then C, therefore if A then C. Now, it's worth noting that what this kind of argument is attempting to accomplish is very much like a categorical syllogism. And in fact, it turns out that these typically translate back and forth from categorical to pure hypotheticals without too much difficulty. But to make sense of this, if you think about it, the conclusion is trying to say that there's a conditional relationship between A and between C, between the antecedent and the consequent in the conclusion. What allows us to draw that conclusion or connect A and C together is, of course, the fact that they share a middle term, just like with categorical syllogisms. A has a connection to B, and B has a connection to C, so A has a connection to C because of that shared connecting term B. So let's look at a very nice example of a pure hypothetical syllogism. So this argues, if a man could not have done otherwise than he in fact did, then he is not responsible for his actions. But if determinism is true, it's true of every action that an agent could not have done otherwise. Therefore, if determinism is true, no one is ever responsible for what he or she does. Now notice in this particular case, the conditional statements are really obvious. Every line has a very clear, blatant conditional assertion, if then, all the way through. Even the conclusion is just a conditional statement. If determinism is true, then no one is ever responsible for what he does. So this should be a good tell that we're dealing with the hypothetical syllogism, and the fact that the conclusion is not a single proposition, but rather its own conditional statement suggests that we're probably dealing with a pure hypothetical. So if we had to look at this in its form, it's basically saying if not O, then not R, if D, then not O, therefore if D, then not R. And notice again, just like with the categorical, what we see is a certain kind of move here where we want to connect the two terms in the conclusion, in this case D to not R. Those things are being asserted to have some kind of relationship, in this case a conditional relationship. And what allows us to move from D to not R is the fact that D and not R are connected in the two premises by way of the shared term, by way of the not O. So what exactly are we looking for in a hypothetical syllogism? Remember, our goal here is not to be able to evaluate these yet. We will eventually do that. We don't want to know if they're good or bad. All we want at this point is to recognize what it is we're looking at. How can you tell that you're dealing with a hypothetical syllogism? Well, the telltale signs here are pretty straightforward. The big things you're looking for are, first of all, clear or obvious conditional statements. If an argument is built around conditional statements, start thinking hypotheticals. It's not a guarantee, but it's very likely. Also keep in mind that if all you have is a single conditional statement, then it's not an argument at all. You're going to have a second premise and then a conclusion that resolves it. So keep in mind that what we're looking for with the syllogism is going to be multiple premises and a single conclusion drawn from it. Now, in a hypothetical syllogism, the telltale signs are, again, first of all, that it's built out of or around conditional statements. And then the other thing, and this will be true for all deduction, or at least all the syllogisms, is that you're going to see a kind of repetition of terms. You'll see the terms repeat themselves. If A, then B, A, therefore B. If A, then B, not B, therefore not A, and so on. You want to see these terms repeating themselves. That's what makes this kind of reasoning work. So those are the sort of things you should be looking for with hypothetical syllogisms. Now, let's move on to the final type of deductive argument that we're going to look at for the class, at least for this module. This is a disjunctive syllogism. The first thing to note about it, like the other two, is that it is, in fact, a syllogism. That means it's a deductive argument, and it means that it will have two premises and a single conclusion that follows from those premises. So the question we have to ask is, what is it that makes it disjunctive? Well, a disjunctive syllogism is essentially a deductive form of argument in which the major premise of the argument is what we call a disjunctive statement. The second premise is going to be simply a denial of one of our disjuncts, and the conclusion of the argument will be an assertion of the truth of whatever's left over. Now, the important thing at this point is to figure out what we mean by a disjunctive statement. So what's a disjunctive statement? This is pretty straightforward. A disjunctive statement is simply an either-or claim, something like either P is true or Q is true. So some basic terminology you might get comfortable with is what is called a disjunct. A disjunctive statement is built out of disjuncts, and the disjuncts are just basically the terms in the either-or claim. In this case, P is a disjunct and Q is a disjunct. Now, unlike a conditional statement that has a natural order to it, an antecedent followed by a consequent, a disjunct can go anywhere, and they're just anything that's in an either-or claim is one of your disjuncts. So the first thing to note about a disjunctive syllogism is that its main premise, the thing that everything's built around, is going to be simply a disjunctive statement. And your disjuncts in that disjunctive statement, just like the antecedent and the consequent in a conditional statement, are also truth functional claims. So if you understood what that means, you can apply the same basic idea here. The A and the B in this case are the kind of things that are either true or false. A is either true or it's false. B is either true or it's false. And just like with a mixed hypothetical syllogism, a disjunctive statement is simply going to start playing around with these truth functions. So notice the second premise is going to typically work by denying the truth of one of the two claims. In this case, notice what it says is A must be false. So the original premise says either A is true or B is true, and A says, well, A is not true, it's false. So we have a denying of one of our disjuncts. And then the conclusion is going to affirm whatever is left over. It wants to say that whatever's left over, once you've eliminated everything else, whatever's left over has to be the case. So this is your standard form of a disjunctive syllogism. The initial premise is simply a disjunctive claim, it's either A or B, and then the second premise works by denying one of the disjuncts in order to affirm whatever's left over. So a very easy way of thinking about disjunctive syllogisms can be had by turning to the game Clue. If you've ever played the game Clue, if you really stop and think about how that game works, it's really just a series of disjunctive syllogisms, 3 different ones running at the same time. Now, the game itself is quite stupid, so if you've never played it, you're probably better off. But if you have, this example will make perfect sense to you. Because what happens in Clue is essentially we take a set of cards, and we'll just stick right now with murderers. Each card has a different potential murder suspect. We shuffle those cards, and then we draw one out of that deck and put it in an envelope. The goal of the game is to figure out what's in the envelope, even though we haven't seen it. And the way we do that is we look at all the other cards. So if there are 8 cards and I see that 7 of them are not in the envelope, I know what has to be in the envelope because whatever's left over has to be that card. And that's basically all you do in a disjunctive syllogism. You have a list of possibilities and then you just start eliminating things so that whatever's left over would have to be the case. So let's take a look at this simple example. Let's say you're playing Clue and you've narrowed it down. The murderer has to be either Colonel Mustard or Miss Scarlet. Right? So one of those two must have committed the murder. And then you discover that Miss Scarlet was in the library at the time of the murder. That is, you see her card is not in the envelope. And so you know that she couldn't have done it. Well, if it's true that Colonel Mustard or Miss Scarlet must have done it, and you know Miss Scarlet didn't do it, then Colonel Mustard must have. That's the only possible explanation, assuming your original claims are true. So notice the basic structure of this is it's either Colonel Mustard or it's Miss Scarlet. And since we discover it wasn't Miss Scarlet, we know, and we know with absolute certainty, that it must be Colonel Mustard. So notice what we have in this case. The basic structure of this argument begins with the main premise of a disjunctive statement, an either-or claim. In this case, we have either Colonel Mustard committed the murder or Miss Scarlet committed the murder. And notice those two disjuncts, the C and the S, are truth functional. They're either true or they're false. If C is true, that means Colonel Mustard did in fact commit the murder. If it's false, then he did not. If S is true, then Miss Scarlet did in fact commit the murder. If it's false, then she did not. Now notice the second premise here works by denying the truth of one of the claims. In this case, it says Miss Scarlett didn't do it. And of course, if that first premise is true, that it has to be one of those two that committed the murder, and we know she didn't do it, then we can affirm as true whatever's left over. This means that Colonel Mustard must have committed the murder. So this is a standard, common way of understanding what a disjunctive syllogism is. Here's another example, again from Sherlock Holmes. It says, I've already said that he must have gone to King's Pyland or to Capelton. He is not at King's Pyland, therefore he is at Capelton. So notice the structure of this. It begins with a basic disjunctive statement. Either the horse is at King Pyland or the horse is at Capelton. And again, both of those claims are either true or they're false. The first claim, the horse is at King's Pyland, is true if the horse is there. It's false if the horse is not, and so on. So we have this first disjunctive statement with two truth functional disjuncts, P and C. The second premise picks one of those and denies it. It says it's not the case that P is true, and that allows us to affirm whatever's left over. Right? So in this case, we know that the horse has to be at Capelton. So keep in mind with the disjunctive syllogism, unlike our mixed hypotheticals, in a mixed hypothetical, we have a conditional statement with two truth functional terms, and your premise and conclusion are going to do the same thing. I affirm and then I affirm. With the disjunctive statement, I deny to affirm or I affirm to deny. So the conclusion will do the opposite of the second premise. So to close out the basics of deductive reasoning, let's stop for a moment and think about what you're looking for with the disjunctive syllogism. Because again, our goal here at this point is not to determine if it's a good argument or a bad argument. What we want to know is how can you tell what kind of argument it is. So what are the telltale signs of a disjunctive syllogism? Well, again, what you should be looking for, pretty much like the others, is that it's built around, in this case, a disjunctive proposition. That is an either-or claim. The rest of the argument is going to work by affirming and denying what's in the original statement. The other obvious telltale sign, which is true for really every one of these syllogisms, is what you're looking for is a repetition of terms. Either A or B, A is true, therefore B is not true, and so on. You want to see those terms repeating themselves. When you see that kind of repetition, it's not a guarantee that it's deduction, but it's very likely. So start paying attention to those kind of structures. The things you should be doing at this point is getting very comfortable with the very distinct basic functional structures of disjunctive syllogisms, hypothetical syllogisms, and categorical syllogisms so that you know what you're looking for. That's what we want in this part of the course. Now, we've finished up with deduction, so we're going to move on to inductive argumentation. Now, it's important to recognize for this class that in the end, we're not actually dealing with induction. We're going to introduce inductive argumentation to you largely as a way of recognizing that there's an entire class of arguments that don't fit into formal logic, and so that you don't confuse yourself thinking that an inductive argument might be deductive. Because what we're doing in this class, in formal logic, is all about deductive reasoning. But we need to understand what induction is, so we need to define it, and then we need a way to figure out how you can tell when you're looking at an inductive argument versus a deductive argument. So what exactly is inductive reasoning? Well, here again is a working definition. An inductive argument is an argument in which the arguer claims, or it is implied by the kind of reasoning used, that it is improbable for the conclusion to be false, given that the premises are true. Now notice the definition here is almost perfectly identical to the definition we saw of deduction. The big difference is the one word that's underlined here. In deductive reasoning, we find that the conclusion follows necessarily. It is impossible for the conclusion to be false if the premises are true. In induction, on the other hand, the best you get is that it's highly improbable that the conclusion is false, but not impossible. In other words, in induction, it's always possible, no matter how good your argument is, that the conclusion might actually be false, even if your premises are true. In deduction, that can't happen. So let's look at the basic characteristics of induction. And again, our goal in this is to get you into a position where you can identify what you're looking at. You can look at an argument and say, I know that this is inductive because it's reasoning in this way, or I know it's deductive because it's reasoning in this way. So here are the basic characteristics of induction. The first point is this: the conclusion of a good inductive argument does not follow necessarily from the premises that are given, but rather the conclusion is only highly probable. That's the best you'll ever get in induction, is a highly probable conclusion. So much so that you might as well accept it to be true. But the point here is that inductive reasoning is never absolutely certain, and it isn't really trying to be. So let's take a look at an inductive argument to get an idea of what we mean here. So take this example. It says, it has snowed in Spokane every single winter for the last 100 years. And so it's very likely the case that it will snow next winter as well. Now notice this argument. The conclusion here it says is that it's going to snow next winter. We don't know if that's true with any certainty at all. We can't say that it's necessary that it's going to snow next winter. All kinds of things could happen to prevent it. Maybe it will be just a freaky warm winter and we're not going to get snow. Maybe the planet will explode and we'll never have a winter in Spokane again because Spokane will no longer exist. All kinds of things are possible so that that's not a necessary conclusion. But in terms of evidence, that's still pretty compelling stuff. If every single winter for the last 100 years we've seen snow in Spokane, it's pretty likely that it'll snow next winter as well. It's not necessary, of course, but it's very plausible, in fact, highly plausible, so much so that you should probably think it will snow. And, if you're debating things like buying good snow shoes or buying snow tires or something for your car, this kind of an argument should be compelling enough to move you, right? But again, the point here is that that conclusion is anything but necessary. It is, of course, possible that what we'll see is no snow next winter. So why induction works like it does is that inductive arguments are always attempting to move beyond the scope of the content of the premises to try to give us new information beyond what is already known in the premises. If you think back to deduction, this is exactly why deduction doesn't work this way. Deduction gives us necessary conclusions because the conclusion doesn't really tell us anything new that we didn't already know from the premise. Right? In the case of induction, what we find is that the conclusion is always trying to give us something more beyond the scope of what is already known in the premises. And the last part of this is actually quite important for understanding induction. As a rule, what happens in induction is this. It uses observation as a basis for asserting a conclusion about something that has not been observed. So if you think back to the snow in Spokane example that we just saw, notice we use observation, in this case historical evidence about past winters and snow, as a basis for asserting something about something that we haven't observed, and in fact that we just can't observe until it happens. We don't know what's going to happen in the future yet. So we're using information from the past to create some sort of basis for asserting judgments about what will happen in the future in this case. Let me give you another example that will show you this point. This argument says there's a scar on his cheek, and as scars are usually the product of lacerations, it seems likely that he was injured at some time. Now notice our conclusion here is that this person was probably injured. And how this argument works is that we are essentially trying to explain something that we didn't see. We didn't see this person get injured. If we watched the person get injured, we don't need this argument. We know he was injured. So what we're doing essentially is trying to form a basis for judging that this person must have been injured at some point. And what we do is we turn to observational data and stuff we know about scars and so on to make this claim. We see the scar, there's a scar that we observed, and we go back to our own experience and understanding of how scars are produced to form the judgment that he must have been injured at some time. Now it's worth noting at this point that there is nothing about this conclusion that is necessary. Right? Of course, maybe the person wasn't injured. It could have been a birth defect. It could be stage makeup. I might be hallucinating. I don't know. But it's a pretty reasonable conclusion to draw based on the evidence that's given there. Okay, and again, notice what this does is it moves from what we observe and know to try to make claims about something that we haven't observed. So the last point to make about informal logic or inductive logic is that when we sit down to determine the merits of an argument, we cannot do so by extracting from the language in which the argument is ultimately constructed. Now what we mean here essentially is this. Unlike deduction, where we can assess an argument's merits by looking simply at the form or structure of the argument, in induction you simply can't do this. If I'm talking about politicians and liars and sinners, in an inductive argument, I need to know something about those things, and I have to work from the knowledge base I have about politicians, liars, and sinners, or scars and lacerations, and so on. So in other words, basically, inductive argumentation is not analytic, and it cannot be reduced to mere form, like we will see with deduction. Now, there are a wide variety of different types of inductive arguments. And we're going to basically look at this list. We'll try to move through this quickly. Again, our goal here is merely to get you to recognize what kind of argument it is, not so much determine if it's good or bad. So here's the list. We have arguments from example, predictions, generalizations, arguments from analogy, arguments from authority, and what I want to suggest, even though the book doesn't do this, is we can break these into two different categories, a genuine argument for authority and arguments from signs, and then finally a causal inference. Now, for what it's worth, the bottom four from generalizations down all the way to causal inferences are really the core of inductive reasoning. The other two tend to be a little amorphous and will often blend into the bottom four. But when we get to generalizations, analogies, authority, and inference, or causal inference, these are very specific types of inductive arguments, and we can spend a little more time working through those than we will with the first two. So let's start with an argument from example. This is an argument that purports to prove something is true by simply giving one or more examples of it. So the basic idea here is I say X is true, and then I give an example that would somehow show that it must be true. So let me give you an example of this. Cal Watson is eminently qualified for the position of sheriff. He has 10 years of military service under his belt and nearly the same as a state's patrolman. On top of this, he's received his bachelor's degree in criminology and is a respected member of the community. Now, if we stop and think about this argument, it's clear that the conclusion here is Cal Watson is qualified for the position of sheriff. Everything that follows, in other words, all of the premises, the various claims made in the premises, are really nothing more than examples of what this person takes to be qualifications for the position of sheriff. So one example of a qualification would be military service, another would be service as a state's patrolman, another is a degree in criminology, and so on. So all of these are simply examples of qualifications for the position of sheriff enlisted in defense of the claim that he's qualified. Now notice in this particular case, what we have to do is sit down and kind of think how pertinent or relevant or important are these various things for determining qualification. If, for example, this argument said Cal Watson is eminently qualified for the position of sheriff because he has really cool sheriff sunglasses and a really big handlebar mustache. Notice that is also attempting to give you examples of qualifications for the position of sheriff, but they're really obviously stupid examples that don't do any work for defending that. So keep in mind with induction, unlike deduction, where we simply go look at the form and work through the structure of the argument, in this kind of stuff, you have to really take your time and think about the relevance and the merits of the kind of stuff offered in defense of the claim. So here's another example. Strictly speaking, when we assert a right for X, whatever X is, we assert that person Y has a duty. But to claim that person Y has such and such a duty presupposes that Y has the capacity to perform this duty. It would be nonsense to say, for example, that a non-swimmer has a moral duty to swim to the help of a drowning man. Now notice in this case, the conclusion is the second line. And that second line basically tells us that to say that someone has a duty presupposes the person has a capacity to do this. And then what we get here is just a kind of hypothetical example of a situation that allegedly shows us that this must be true. We wouldn't say of a non-swimmer that they have a moral duty to swim. It doesn't make any sense. And so what that does is it takes that example as a way of proving this more generalized claim. So the second type of inductive argument that we're going to look at, again, that's a little more amorphous and will often blend into other types of inductive reasoning, is what we call a prediction. And a prediction is exactly what it sounds like. An argument for prediction is an argument that reasons from our knowledge of events in the relative past or in the present in order to make claims about future events that we have yet to experience. So the Snow and Spokane example that we've seen is a great example of a prediction. Notice what it's trying to do is tell us something about what will happen in the future, something we haven't observed and we can't observe until it happens. And it's using past experience with Spokane winters as a way of forming a rational judgment about it. So it's predicting what will happen in the future by looking at past experience. Another example, and if you think about it, we reason like this all the time. So we have good reason to think that tomorrow we can catch the train at precisely 6 a.m. This transit system is well known for its reliability, and every time I've ridden the train in the last few months, it has been right on time. So notice the conclusion is tomorrow the train will be here at 6 a.m. And our evidence for this is, you might say, public experience in the past with it, which leads to the conclusion that it's reliable, and your own personal experience in the past of riding the train where it was always punctual and on time. So we're basically forming a judgment about what will happen tomorrow morning by looking at what has happened in the past. This is how a prediction works. So a generalization is, again, going to be a little more specific in terms of an argument type. And we can narrow this down and kind of frame it in a more concrete way than we did the first two. So basically, a generalization is an argument that proceeds from our knowledge of a selected sample of a population to make generalized claims about the whole population. Now, the first thing to note about this is, what do we mean by a population? It's easy to get hung up on the term and start thinking of populations of human beings, like people in Spokane or people in Cheney, Washington, or something like this. But when we're talking about a population in this kind of reasoning, what we mean is any collection of things. So it could be quite literally anything. Pencils in a Walmart store. It could be fish in the lake of Coeur d'Alene. It could be wine glasses in the state of California. Anything at all would constitute a population. And what a generalization does is it looks at some of that population and it uses what we know about that population sample as a way to form claims about the entire population. So the idea of a population, again, is very important to understand. When we talk about populations, don't get hung up on human populations. It means quite literally just anything, any collection of things that you want to generalize about. So the basic move that we get here is really twofold. There are kind of two different ways in which we generalize or use generalizations to reason. The standard way, the classic generalization, essentially takes a selected sample of a population, and then it gleans some information about that. We know something about that sample, and then we use that as a basis for forming judgments about the entire population, which we haven't actually looked at. We've only looked at some of it. So basically we say something like, we know as a premise that property X is true of this sample of the population. And then we use that as a basis for forming the conclusion that property X is very likely true of the whole population. This is how a generalization works in its classic form. Now, it's worth noting that you can also generalize in the other direction. That is, you start with what is generally, though not universally, true. We generally know that X is the case, for example, and then we say, well, this particular sample of the population is probably going to participate in what's generally true of the whole population. So, formally stated, it looks something like this. We reason from the premise that we know property X is generally true of this entire population, whatever it is. And so the conclusion we draw is that property X is probably going to be true of this specific sample of that same population. So this basic structure is incredibly useful. It's something to pay attention to. In either direction, what we're doing is generalizing. So let's take a look at some examples here. We'll start with this one. The first thing to note about this is that this is not a good argument. It's actually quite weak. But it is really common that people reason in this way, and it is nonetheless this type of inductive argument. It is a generalization. So the argument says, Volvos are not reliable automobiles. My uncle and my brother both own Volvos, and they had loads of trouble with them. So notice the basic conclusion here is that Volvos are not reliable automobiles. We're making a general claim about the entire population or class of Volvos. And the evidence we're using to draw a conclusion about every Volvo out there is the fact that two of them were not very good cars. So because that sample of the population of Volvos, these two that I know something about, were not good cars, Therefore, we have reason to think Volvos in general are not good cars. Let's go the other way around. Let's say it's true that we know that 90% of human beings are right-handed. So 9 out of 10 people are going to be right-handed. We can therefore conclude that John is very likely going to be right-handed, or at least there's a 90% chance of it. It's not a guarantee for sure, but if you had to guess, odds are better that he will be right-handed than he'll be left-handed. Now, of course, that's assuming a great many things about how you gathered this sample of the population and on and on. But our goal is not to actually assess these kind of arguments. At this point, we just want to recognize how this kind of argument works so that we can point at an argument and say that's a generalization. So notice how that works. We know that as a general rule, not a universal rule, but as a general rule, most human beings are right-handed. So this one person that is also a human being that fits into the population of human beings is probably right-handed too. So take this example. Let's say we polled the students at Gonzaga University and we found that 85% of them believed in God. The conclusion drawn here is that it's likely that 85% of all the students at Gonzaga believe in God, within a margin of error. If you stop and think about it, statistics are really just a form of generalization. What we do is we go out and gather a sample, polling sample of some population. In this case, we would say Gonzaga University students. And then from that, we attempt to generalize to the entire population of students as such, right? Now, whether these are good arguments or bad arguments is not important for our purposes, unfortunately. But this is simply a generalization. And statistical reasoning like this is really just a form of generalization that is usually very carefully done. Notice, too, that this example is clearly a worse argument. Hopefully, this will be obvious to you. But it's also just generalizing. It's taking a sample of a population, and then from that, it's universalizing. So this says 85% of the students polled at Gonzaga said they believed in God. It's therefore likely that 85% of all university students in the country believe in God. Now, this is clearly not a good argument, or at least I hope you recognize this, because what is true of one university is probably not going to be something that transfers to all universities. It's too narrow of a scope, right, in terms of trying to generalize from that. But it is nonetheless a generalization. What we have is a sample of some university students in the country, in this case only taken from Gonzaga, and then we're trying to generalize to claims about the entire population of university students in this country. So this is how a generalization works. Again, it moves in one of two directions. Either we take a sample of a population and glean some information about that. We know that something's true about the sample, therefore it must be true about the entire population, or we go the other way around. We know what is generally the case about a population, and then we try to apply that to specific instances of that population. So the next type of inductive argument we have is an argument from analogy. These are very important arguments in philosophy, for what it's worth, and they're very powerful arguments when they work. They can fail in many, many different ways, but when they work, they are really, really quite compelling. So how does an argument from analogy work? So the basic definition here is, this is an argument where the reasoning depends on the existence of a similarity between two things or different states of affairs. In other words, it's an argument that compares one thing to another, and it uses the similarities between those different things as a way of forming judgments about one of them. So analogical reasoning is the kind of reasoning that depends on a comparison of instances. And it turns out that if the instances that we're comparing are sufficiently similar to one another, then generally speaking, the conclusion is typically a strong one. So at this point, we're going to move away from the book a little bit. And I want to suggest to you what I take to be the most clear and coherent way of understanding what an argument from analogy does. These are, again, very powerful arguments, and no matter how messy or complex your argument from analogy is, in the end, you can basically smush it down into this basic form. Right? What you'll get are two premises and a conclusion. The first premise is basically just the analogy. So it is really just saying that there are two things and they're alike in certain ways. So we would say something like object X and object Y are similar to one another in that they share in certain properties. Let's say Q1 and Q2 and maybe Q3 or whatever. So there's the first premise. That is the analogy itself. We have object X, and I'm comparing it to object Y, and I assert in that premise that they're alike in certain ways. The second premise is going to take up one of those two terms, and it will assert that it has some distinct property. So notice, premise 1 says X and Y are alike in that they share in Q1 and Q2, and we know X has property P, and since X is like Y in all of these other ways, we can then conclude that Y probably has the same property P. So this is a basic structure of how arguments from analogy work. This is a really powerful tool if you're ever working with analogies to kind of get it into this basic form, because you can start to see exactly where it starts to fall apart when it's a bad argument, and you're in a pretty good position to confirm that it's a good argument as well. So let's take an example here of an argument from analogy. This is from Thomas Sowell. He says, because courts have ruled that women have a legal right to an abortion, some people have jumped to the conclusion that the government has to pay for it. You have a constitutional right to privacy, but the government has no obligation to pay for your window shades. So let's break this argument down according to the method that I just showed you. So if you think about it, what Thomas Sowell is trying to compare there, or the basic analogy of this argument, is to compare abortion and privacy. On one side, we have abortion, which is a constitutionally protected right, and on the other, we have privacy, which is also a constitutionally protected right. So notice what we have are two different things that are alike in a certain way. They're analogous to one another in the sense that they're both constitutionally protected rights. The second premise takes up one of these, in this case, the premise, and notice we know he's going to claim about privacy that the government doesn't have to pay to ensure that you can exercise that right. We don't have to buy you window shades so that you can have your privacy. That falls on you, he claims. So pay attention here what just happened. In the second premise, we're going to go with something we know about one of the two, in this case, of our analogs in the analogy, in this case privacy, and we say we know that this property has to be true about it. And then the conclusion we draw is about the other one, in this case rather clearly abortion. What he's going to say is, if that's true, if it's true that with privacy, which is a constitutionally protected right, that the government doesn't have to pay to ensure that you can practice that, then shouldn't it probably be true about abortion as another constitutionally protected right that the government doesn't have to pay to ensure it? Now, whether this is a good argument or a bad argument is not so much a concern at this point, but the structure of the argument is very important here. This is how analogies work. Right? Let's take up another example. So let's take a look at a second example, in this case from Thomas Friedman, where he argues, why would Republicans, the party of business, want to focus our country on breathing life into a 19th century technology, fossil fuels, rather than giving birth to a 21st century technology, renewable energy? As I've argued before, it reminds me of someone who, on the eve of the IT revolution, on the eve of PCs and the internet, is pounding the table for America to make more IBM typewriters and carbon paper. Typewriters, baby, typewriters. So if we want to make sense of this argument, the first step is to figure out exactly what the analogy is. What is he comparing to what? And so notice what he's doing here is he's saying on one side we have the Republicans' push to basically mine for more fossil fuels, and he's comparing it to a hypothetical scenario of a push to making more typewriters. Now, what these two things have in common, what we know is true of both, he's saying, is that both are just outdated technology, and there's something better, some new technology just right there on the horizon. So the second step in his argument then is to basically say, we know that if there was someone on the eve of the IT revolution and PC computers and so on, who's out there demanding we make more typewriters, we know that would be really bad public policy. And so what he's basically trying to argue here is that the same is probably true of the push for mining for more fossil fuels, right? If it turns out that a push to make typewriters is bad policy, and primarily because it's dated technology and there's something better on the horizon, and if fossil fuel is exactly the same on those points, then isn't it probably bad public policy as well? That's essentially what he's arguing. Now, we would have to consider all kinds of things to determine if this is a good argument or bad argument and so on. But again, for our purposes, it's good enough to just understand the foundational structure of argumentative or arguments from analogy and how they work. So this is something that's worth spending a little time with to figure out. But again, we're not actually dealing with this directly in the class. So the next type of inductive argument we have to consider is what is called an argument from authority. Now, an argument from authority is a really simple type of argument. This is an argument where the justification for the conclusion rests simply on the statement of some presumed authority or witness. If you want a really easy way of understanding it, these are the because I said so arguments. That is, it's true because some authority, some expert or the like said it was true. And that's really all there is to an argument from analogy. Now, frankly, on the surface, these sound like really dumb arguments, and often logic has been very critical of these. But let's be honest, we use these all the time, and in fact, in many cases, there's not much else we can appeal to. So they're important arguments for us. We reason this way, constantly, and frankly, we reason this way quite often in very profound, useful ways. Now, here's an example of how this works. Clearly, Naomi Klein is a very intelligent person. In 2005, Klein was ranked 11th place in a 2005 Global Intellectual Poll, a list of the world's top 100 intellectuals compiled by Prospect Magazine. Now, if you stop and think about this argument, what it's basically asserting is Naomi Klein is very intelligent. And the only actual evidence we have for that claim is that Prospect Magazine said so. There isn't much more to it than that. Now, if it's a good argument or bad argument, we'd need to know a lot about Prospect Magazine, how they gathered their data, what judgments they're making, are they biased, and on and on. But in the end, the argument is really simple. It's true because they said so. There's not much more to it. Here's another example. Although this one also involves a bit of mathematical reasoning, in the end, it ultimately just boils down to someone said so, therefore it's true. So this says the CEO of Avista announced today that the price of natural gas will increase 30% this winter. Given this, and assuming that I use the same amount of gas this winter as I did last year, it seems safe to conclude that my heating bill will be larger this February. Now notice, there is certainly some mathematical reasoning here. To get to this conclusion, we would have to have that, and that is deductive. But in the end, the reason we think it's going to be more expensive boils down to the fact that the CEO of Avista announced that the price of natural gas is going up, and therefore we think it's going to cost more. That is, at its core, all there is to this argument. So an argument from authority is actually quite simple. They're very, very basic kinds of arguments. In the end, they just amount to saying it's true because someone, some group, some organization, some authority of some sort said so. An argument from signs is not much different than this. In fact, what I generally see these two is just a sort of variation on the same thing. The book will distinguish between them, but frankly, the methods for evaluating signs and authority are basically the same. You can think of this as kind of an argument from the authority of some physical evidence. Quite often, quite literally a sign, but it can be other things as well. So definitionally, it runs something like this. This is an argument that proceeds from our knowledge of a sign to the claim about the thing or situation that that sign symbolizes. Now, this is also something we do all the time, and quite rationally so. An easy example would be something like this. The road sign we just passed said Seattle is only 20 miles away, and so we must already be in Washington. Now notice, this also presumes you have some knowledge about the geography of Washington, where Seattle is located and so on. But if that sign is correct, and it says that Seattle is only 20 miles away, then it's quite plausible to assume that we are in fact in the state of Washington, because 20 miles in any direction from Seattle is going to be in Washington or in water. Now notice, if you're driving along and you see the sign that says Seattle, Washington, 20 miles away, and then you look out your window and you see the Eiffel Tower, you might stop to wonder if there's something wrong with that sign. And notice this too, the conclusion you would draw that that sign must be wrong is based on another argument from signs, because the Eiffel Tower also is essentially a kind of physical piece of evidence, and what it signifies is in fact Paris. So if you see the Eiffel Tower, then you have good reason to believe you're probably in Paris or maybe in Vegas. In either way, you would have no good reason to think that you're near Seattle. Another example would be something like this. A bear must have recently passed this way because there are fresh bear tracks in the snow. The simple fact here is, when you see bear footprints, the most plausible account of what that means or symbolizes is that bears stepped into something. So it's a good reason to imagine that there is probably a bear somewhere in the area. Now, of course, it doesn't have to be the case, right? It could be that you're camping with someone who has bare footprint slippers and they went out walked in the snow. You could be hallucinating or something, but bear footprints very likely imply a bear walked in that area. Notice too, if you see signs like these, your mind should quite rationally jump to some conclusions. If you're about to walk in a room and you see, let's say, any one of these signs, you might stop and wonder if you're about to walk into something dangerous, because every one of these signifies potential danger of some sort, radioactive danger, poisonous danger, and stuff like this. So these kind of things are arguments from sign. If I see a sign with the radioactive symbol on it and I draw the conclusion that something is probably radioactive, then I am reasoning by signs. Now, the final type of inductive argument that we're going to look at is a causal inference. And by causal, we mean simply cause and effect. When we argue about cause and effect relationships, we are reasoning inductively. So this kind of argument basically works in a number of different ways. The core of this is really simple. This is an argument that proceeds from our knowledge of a certain cause to draw conclusions about the effects that it'll have, or from our knowledge about some particular effect to draw conclusions about what must have caused it. So the basic foundation of this kind of argument is that it's built around a cause and effect relationship. And we reason about causality in essentially three different ways. And so what I want to do is basically lay out formally what these three different ways are, then we'll look at a couple examples. So again, keep in mind, it's a cause and effect relationship that sits at the heart of this kind of inductive reasoning. So the first way in which we reason about causality is pretty straightforward. We go from a known future event to predict the effect of that event. Right? So notice what we have is a presumed understanding of a certain cause and effect relationship. The cause and effect relationship itself is already something we claim to know. And then we say, well, I know I'm about to do this thing. And since I know this thing causes this other thing, I can predict what will happen in the future. So to give you a simple example of this, if you walk up to a light switch, we know that light switches have a causal relationship to turning on and turning off lights. So if you walk up to a light switch and you're about to flip that switch and you predict what's going to happen, what you will see essentially is, because we know that this light switch will turn off lights and I'm about to flip it, therefore the light should turn off. That's one way in which we reason about causality. We start with the presumption that we already know a cause and effect relationship, and then we reason from what we know we're about to do to predict the effects of our actions. We can also go the other way around. This is also rather commonplace. And notice with number 2 here, we also start with the presumption that we already know a cause and effect relationship. I know that A causes B. And then what I do is I observe B. I observe something. And since I know A causes B and I see B out there, then I can reason backwards to say, well, A must have caused it. So what I do is I go back to establish the cause of some event that I have observed based on my knowledge of a cause and effect relationship. The final way in which we reason about causality is where causality is not presumed to be known. What we do is we use observation to try to establish a cause and effect relationship that we don't know at this point. So in this case, the conclusion is in fact going to be a cause and effect relationship. In the first two instances, number 1 and number 2, we start with the premise of causality. We assume A causes B, and then we either reason from A to try some conclusion about what's going to happen, or reason from B to try to establish what must have happened before. But in 1 and 2, we start with a premise that claims we already know A causes B. In number 3, we don't know what the cause and effect relationship is, and our conclusion is going to be something must be causing something else. So a good or easy example of this would be if you walk up to a light switch and you flip it and the lights turn on, then you flip it down again, the lights turn off, and then you flip it and it turns on again. You do that a few more times, you might start to draw the conclusion from that observation that that light switch turns a particular bank of lights on or off. So here are some examples of inductive argument types. This one's kind of a goofy one, but it works. It is likely that Paul was abused as a child. Notice what we're trying to do is draw a conclusion about some earlier or prior causal event based on what we observe here. So it's likely Paul was abused as a child. He is abusive towards his own son, and abusive parents have usually experienced abuse during their own childhoods. Now, it's not really true for what it's worth, but if you think about the basic structure of this argument, this is saying being abused in your youth will cause you to abuse your own children. And then it says, we know that Paul is abusing his own child. Therefore, we can reason backwards, this is number 2, to claim that Paul was probably abused as a child. One last example, then we'll call it good for this particular video. A recent report says that country music might trigger suicide. Cities in which more country music is played on the radio have significantly higher suicide rates, according to a study that compared the suicide rates with country radio's market share in 49 metropolitan areas, including Nashville. Country music reinforces thoughts of hopelessness amongst potential suicide victims, that things are just not going to get better and you have to adjust to these miserable conditions, said the co-author of the study. Now notice the conclusion here is that country music has a causal relationship to suicide. It can cause suicide. The reason for this is we observe a correlation between two things. We observe that there's more country music played in cities, we will see higher suicide rates. Where there's less country music, we see less or lower suicide rates. And the conclusion drawn from these observations is that country music must be causing suicide. Now notice, of the 3 different types that we looked at, this is number 3. We're trying to prove a cause and effect relationship. The cause and effect relationship is the conclusion we're drawing. And for what it's worth, it's a terrible argument. Hopefully you recognize that. But since we're not dealing with causality, we don't really, or inductive reasoning, we don't really need to go through this. At this point, you just need to understand the various types of inductive arguments, how they work, what the kind of mechanics are to induction and deduction, and try to get comfortable with recognizing what you're looking at when you see it. So that's the end of this particular video. Again, this covers section 1.3 in the book. If you have any questions about the material in this section or about the class or anything else, again, feel free to contact me. I'd be happy to meet with you via Zoom, or we can talk about it through an email.